We can use experimental data to figure out what the chemical formula is. We're limited here to the empirical formula, which is the lowest ratio of the elements. We can do this in a couple of ways. We can look at the masses of elements that were formed when we decomposed a compound, or we can look at the masses of elements that reacted to form a compound, and we'll be doing an experiment like this in lab, or we can look at the percent composition that was determined experimentally and figure out what the formula is from that. So again, important to remember what these ratios are. The empirical formula represents a ratio of atoms or a ratio of moles of atoms, not a ratio of masses. It's the individual atoms. So these calculations have several steps. Each of the steps is pretty simple. One of the hard things I remember was just remembering what am I supposed to do next. So you got to practice these. The first thing is you need to start with the masses of each element present in whatever sample of the compound you're looking at. Sometimes you'll be given the masses. Sometimes you'll be given a percent composition. If you have percent composition, you can turn that into a mass very easily by saying, well, what if I had 100 grams of this? Then the mass would be the same as the percentage, and so you just write it down that way. The next step is converting those masses into moles, because we need to find the ratio of the moles of particles, not the masses. And then your book talks about writing a pseudo formula. You're welcome to do that. I think that's just kind of an extra step, so I typically don't do that part. What we want to do is we want to divide all of the moles that we end up with. If you're doing the formula, it would be subscripts, but divide all the moles by the smallest number of moles. And sometimes those ratios will be whole numbers. Other times they will not. This is my guideline. It could vary if you go to a different class. If that ratio you come up with is within 0.2 of a whole number, if it's 2.15, that's within 0.2 of a whole number. Then you can round it to a whole number. If you get 2.25, that's too far, you can't round that. If you don't get whole numbers, then you have to multiply all of those to get whole number subscripts. This will become hopefully more clear when we do an example. So if it's not making sense right now, don't worry, it'll come. If you recognize the fractional equivalence the decimal equivalence of fractions, then you can anticipate what you should multiply by. If you have 2.25, then you should multiply by 4, etc. You can also do the trial and error method where you just try 2 and try 3 and try 4 and see what gets you a good result. So let's do an example. So always good to read the question. Sample of a compound is decomposed in the laboratory, produces 165 grams of carbon, 27.8 grams of hydrogen, and 220.2 grams of oxygen. Calculate the empirical formula of the compound. So the first thing is we need masses of each element. Those were given to us. So we're going to write them down. And I just do them in the same order. So here's 165 grams of carbon and 27.8 grams of hydrogen and 220.2 grams of oxygen. We need to convert these masses to moles and then find the smallest ratio of the moles. So I'm going to use the molar masses for the elements. So I'm going to put moles of carbon on top, grams of carbon in the bottom. 1 mole of carbon, not 12. It is 12, not 16. 12.01 grams. Just watch what I write, not what I say, I guess. So that's giving me a big mess. Here, you don't need to write down all the numbers, but keep, at minimum, the correct number of significant figures, and I highly encourage you to keep 2 extras. This would have 3 sig figs. So 13.7, and just write down the 2 next digits. So that's the moles of carbon. And then we're going to do the same thing for the other elements. We're going to use the molar mass to convert the mass into moles. So 1 mole of hydrogen, 1.008 grams. This gives me 27.579. And if I screw up on one of these calculations, please just yell at me. And then the oxygen, 1 mole of oxygen for every 16 grams of oxygen. .7625 moles of oxygen. Any questions? I had 3 masses, different elements. I'm using their molar masses from the periodic table to convert the grams into moles. Now I want to find the lowest ratio of these. The book says make a pseudo formula. Well, I prefer to just leave them here, and what I'm going to do is I'm going to identify which of these is the smallest number. Well, it's the moles of carbon, right? This is a teeny bit smaller than the moles of oxygen. So what I'm going to do is, this is the smallest one. I'm going to divide all of them by the smallest one. So this one gets divided by itself. And this one gets divided by 13.738. And this one gets divided by 13.738. So what I'm really doing here is, I'm dividing by moles of carbon, moles of carbon, moles of carbon. So I'm finding the how many moles of each of these elements per mole of carbon. Well, this top one is going to come out to exactly 1, right? Because it's a number divided by itself. So that one's 1. 27.579 divided by 13.738. This is equal to 2.007. And the one on the bottom, 13.7625 divided by 13.738. 1.002. What I'm trying to find here are whole numbers, small whole numbers. These are extremely close to whole numbers, definitely within 0.2, right? So I can round those. So I can round this to 1, and I can round this to 2, and that one is just 1. Those are the subscripts in my chemical formula, my empirical formula. So I'm just going to put the first element first. Carbon had a subscript of 1. We don't write the 1. Next is hydrogen, subscript of 2. Next is oxygen with a subscript of 1 that we don't write, and there's the empirical formula. Any questions? So let's do this one. Here we're given percent composition. Ibuprofen has the following mass percent composition. What's the empirical formula? Ibuprofen. This is, as a mom, this is my go-to medicine. You've got a sore throat, take some ibuprofen. You sprained your ankle, take some ibuprofen. You've got a headache, take some ibuprofen. I don't even know why my children come and ask me anymore, because it's always the same. Take some ibuprofen. Works for all kinds of things. So I need masses of elements. What I'm going to do is I'm going to say, I can choose any size sample, because the percentages in the formula do not depend on the size of the sample. I'm going to choose something that's easy. So I'm going to choose 100 grams. Because if I choose 100 grams, then 75.69 grams are carbon, 8.80 grams are hydrogen, 15.51 grams are oxygen. So all I have to do is, instead of writing percent, write gram. So 75.69 grams of carbon, 8.80 grams of hydrogen, and 15.51 grams of oxygen. And this is where things, begin to get a little repetitious. Convert the grams to moles. So 1 mole of carbon, 12.01 grams. This is 1 mole of hydrogen, 1.008 grams. That's not equals, that's times. And oxygen, so I've got 75.69 divided by 12.01, and that's giving me 6.302, and oxygen 8.80 divided by 1.008, 8.730, 15.51 divided by 16. This is 0.969375. Everybody okay? I could take these numbers and make them subscripts in a formula, but the correct formula has whole number subscripts, right? And I can't just round these off to whole numbers. So what I'm going to do is I'm going to find the ratios. I'm going to divide all of them by the smallest. Here, the smallest one is the oxygen. So that's going to come out to be 1. I want to divide by the smallest because that way I'm ensured that all of my numbers will be 1 or larger. I don't want to make any more fractions. That just makes more mess. So this one comes out to be 9.0058. This one $6.5013. You guys getting those same numbers? Well, we always end up with one that's 1 because we set it up that way. This is close enough to 9 that we can round off. What about this one? Can we round that to 7? No. That's like exactly in the middle between 6 and 7. So what I'm going to do is I'm going to multiply all of these by the same number and try to get whole numbers. Well, you might recognize that 0.5 is the same as a half. So if I multiply by 2, I'm going to get a nice whole number. If you don't recognize that, just try 2. If that doesn't work, try 3. Try 4. Usually you don't have to go that far. So there's my 6.501, and I'm going to multiply by 2 and see what I get. Oh, very nice. 13.003. Bingo. This one was close enough to round. When we multiply it by 2, it's still going to be close enough to round. 18.01. And this one multiplied by 2 is going to be 2. So this is 18. This is 13. We have to come up with whole numbers because you can't have part of an atom. In one molecule of ibuprofen, you can have one oxygen atom or 2 oxygen atoms, but you can't have 1.5. That's like a family with 2.4 children, right? It might be that on average, but nobody has 2.4 children in their family. So we need to get whole numbers, but we need to keep the ratio the same. So this is a ratio of 13 to 18 to 2. That can't be simplified, right? If you try to simplify it, you get something like 6.5 to 9 to 1. So those are our subscripts. For carbon, the subscript is 13. For hydrogen, it's 18. And don't be disturbed that those are large numbers. It's okay. Oxygen is 2. That's the formula for ibuprofen. Any questions? The molecular formula is some multiple of the empirical formula. Sometimes they're the same, but oftentimes the molecular formula is just a multiple of the empirical formula. So if we know the actual molar mass of the compound, we can calculate the molecular formula from the empirical formula. Because the molecular formula is equal to the empirical formula times some number, 1, 2, 3, 4, 5, etc. We can figure out what that is by taking the molar mass of the actual compound, that would have to be given to us, and dividing by the empirical formula mass. So we look at whatever the empirical formula is and calculate the molar mass based on that, and then we divide and we should get a nice number. Let's do an example of this. A compound has an empirical formula, CH, and a molar mass of 78.11 grams per mole. What's the molecular formula? Well, what's the formula, what's the mass of 1 mole of CH? Well, it's 12.01 plus 1.008, right? I think that's 13.018. So 1 mole of CH would weigh 13 grams. The molar mass of this compound is 78. So obviously the empirical and molecular formulas are not the same. What we want to find out is what do we need to multiply 13 by to get 78? I don't know about you, but that's not obvious to me. So to find this number that we want to multiply everything by, I'm going to take the 78.11 grams per mole, divide it by 13.018 grams per mole. I'm going to find out how many times does 13 go into 78. My calculator is saying 6.00015, blah, blah, blah. This should always come out to a nice number, really close to a whole number. We're never going to have to multiply this by anything. If this comes out weird like 6.5, you screwed up somewhere else, go back and look at that, or the problem itself was wrong. So this is 6. This tells me that the molecular formula weighs 6 times as much as the empirical formula. And it does that because it has 6 times every atom. So we've got that CH, and we're multiplying by 6. But that's not how we express formulas. So it's C6H6. Whatever the subscripts in the empirical formula are, you just multiply them by this number you came up with, and you get your molecular formula. You can double check that then by finding the molar mass of C6H6, right? And you calculate that and you'll come up to 78.11. So we've talked about what to do with data from these experiments. How do they actually calculate these things? You know, so you've got some pure substance and you want to know what the formula is. How do they do that? Well, one technique is by burning it, combustion analysis. And this works really well for organic compounds containing carbon, hydrogen, and oxygen. So you weigh the sample, and then you burn it, and you collect the things, the gases that are given off, and you weigh those. So in a compound containing carbon, hydrogen, and oxygen, when we combust that, all the carbon goes into carbon dioxide, all the hydrogen goes into water, and we can figure out the mass of oxygen by subtraction. So here's an illustration of a combustion analysis setup. So we put our sample, we weigh the sample, we put it in a furnace, and we've got lots of oxygen coming in here. And so we ignite this, we burn it, literally. This forms carbon dioxide and water, vapors. Where are they going to go? Well, oxygen's coming in here, they're going to be pushed out the other side, and we're going to make those gases go through two different tubes. And in these tubes, we're going to have a substance that absorbs water and one that absorbs carbon dioxide. So before you start this, you weigh the tubes. Afterwards, all of the water that came through here gets stuck in this absorber. So the tube weighs more. So we can figure out what mass of water came off of that. All of the carbon dioxide gets stuck here. Everything else would go through. So let's look at an example. I'm going to do this one. The other one was simpler. This is more complicated. So upon combustion, a 0.8009 gram sample of a compound containing only carbon, hydrogen, and oxygen produced 1.6004 grams of CO2 and 0.6551 grams of water. Find the empirical formula. So we look at this and we say, well, what do we need for an empirical formula calculation? We need the mass of each element, right? Here we're given masses of compounds. So we need to recognize that the carbon in that CO2 is the carbon that was in the sample. The hydrogen in this water was in the original sample. So we have to take this mass of carbon dioxide and find the mass of just carbon. And for the water, we find the mass of hydrogen in that mass of water. And then we can start. Okay. So 1.6004 grams of CO2. In order to convert this to grams of carbon, I need the molar mass of CO2. So I'm going to convert this to moles of CO2. And then looking at the formula, I can figure out the moles of oxygen per mole of CO2. How many moles of oxygen are in 1 mole of CO2? 2. 2 moles of oxygen per 1 mole of CO2. And we can calculate the molar mass of oxygen. And we see how our units cancel out. And I get moles of oxygen. And then we can convert that to grams of oxygen. But let's stop and think about, what did we do in the empirical formula calculations? We took the mass of the element and turned it into moles of the element. So if we stop here, we're going to have moles of the element, right? So let's just stop there and write that down. 1.6004 divided by 44.01 times 2. Zero 0.0727. I want to keep 4 sig figs. 7272. Here's 4 sig figs. 89. That's moles of oxygen. Bless you. And then I'm going to look at the water. I've got 0.6551 grams of water. Similar process here. I'm going to find the moles of water. And then the moles of hydrogen. How many moles of hydrogen in a mole of water? 2. It's kind of coincidental that they're both 2. Why do we not care about... Okay. I screwed up in that first one. What did I do wrong? Do I want moles of oxygen? No. I want moles of carbon. I was just going to say, why don't we care about the oxygen in this? Because we were pumping oxygen in there so it would burn. I don't want moles of oxygen. I want moles of carbon. So let's fix that. So then I have to change the number too, right? Because there's only 1 mole of carbon and 1 mole of CO2. And then this is wrong. This is why you use pencil. My calculator's arguing with me. Yeah. Zero 0.0363644 moles of carbon. Okay. The bottom one, 0.6551. I need the molar mass of water in here, right? And then this one is times 2. So I'm getting 0.0727. It's my dry fingers trying to move the screen around, and I end up writing on it instead. Moles of hydrogen. But there's another element, right? This compound contains carbon, hydrogen, and oxygen. I found moles of carbon and moles of hydrogen. What about the moles of oxygen? Well, we were pumping all kinds of oxygen in there, so the moles of oxygen in these compounds doesn't give us any information about the moles of oxygen in the original compound. But could I figure out the mass of carbon and the mass of hydrogen? Yeah, I could. I'm going to leave these numbers here because we're going to use those. But we also need to look at the grams. So for carbon, 12.01 grams of carbon per mole of carbon. That is 0.436737 grams. And I'm going to figure out the mass of hydrogen. This is the mass of carbon in that sample. This is the mass of hydrogen in that sample. Do these two masses add up to 0.8009? No, because what's missing is the oxygen. So we find the mass of the oxygen by subtraction. So we've got our total sample mass was 0.8009 grams. And we are going to subtract 0.436737 grams of carbon. And we're going to subtract 0.073289 grams of hydrogen. And I get 0.290873, and that's my mass of oxygen. Any questions? This is the total mass of all three elements. I was able to calculate the mass of two of the elements. I can't calculate the mass of the third from any other data, so I subtract to find out, well, the oxygen is the part that's missing. Grams of oxygen, to calculate the mole empirical formula, I need to turn that into moles. Moles of oxygen. This is a great example of why it's important to be able to show your work and write stuff down so it makes sense. This one would be really, really tough to do in your head. I wouldn't even try it. I've got moles of carbon, moles of hydrogen, moles of oxygen. That's what I need for my empirical formula. I'm going to pick the smallest of them and divide all of them by the smallest. The smallest happens to be the oxygen. So that one's going to give me 1. And I'm going to divide this by 0.018175. I'm going to divide this one by 0.018175. So for carbon, when I do that ratio, I get 2.001. And for hydrogen, I get 4.0004. So this is equal to 2, then this is equal to 4, and then I've got a 1. So those are my subscripts. That was kind of messy. I'm going to... We talked about how do you know which element to put first in a molecular compound. Actually, all you need to do is follow the same order that they were given to you, because they just give them to you in the correct order. And I wouldn't mark it wrong if you put them in the wrong order. So carbon has a subscript of 2, hydrogen has a subscript of 4, oxygen has a subscript of 1, which we don't write. There's the empirical formula. Any questions?
Is the reason why we place hydrogen cheaply in the middle because it has better bonding ability?
That's a good question. Why do we put hydrogen in the middle? Because that's what organic chemists do. Yeah, we don't want to go into why. I'm sure there's a reason. You have a question? Okay. Now this problems like this, these are challenging. Just because of all the little details and all the little steps. Can you pass the class without being able to do empirical formula from combustion analysis? Definitely. You can pass the class without combustion analysis. If you want to get an A, I can pretty much guarantee there's going to be one of these on the exam. So if you want an A, you better figure it out, right? Now, calculating an empirical formula from just masses of elements, that's more important. But that is also easier than this one. These are just icky.